Now, as just a little extra, I've added a graph here, okay? The first graph is of the time spent on land. Now remember that expression was this. So the first graph is just a graph of this function. And it comes up and increases rather slowly. As x goes from 0 to 200. Okay? Now the closer x is to 200, the longer it's going to take the lifeguard, obviously, to get there. This graph isn't overly accurate, but the time to go directly from here to here is about 8 seconds. Time to go from here all the way to here at the 200-meter mark is about 34 seconds. So time on land ranges from 8 to 34 seconds. Now, the time spent in the water decreases as we get over here. So it starts with quite a bit of time spent in water, but then that time decreases. Again, the graph is not very well drawn to scale because actually the time in the water decreases from 150 seconds to about a little less than half that. It doesn't really decrease to half the way I've drawn it. Still, the basic curve has this shape, and that curve keeps decreasing. Now, I had a point drawn here, and I kind of missed it. But that curve more or less levels off, comes close to leveling off at the end. But no matter how far you go, it's never going to actually level off. And actually, if you go past the 200-meter point, the time in the water is going to start increasing again for reasons that you ought to understand. Okay, now you put these two times together and add them, you get this graph, okay? And this graph represents the total time. Now, we notice that this graph is decreasing, but it's getting pretty close to leveling off here. While this graph is still increasing, and this graph is increasing faster than this one is decreasing at this point, and that's going to result in a low point here. Okay? The rate at which this one decreases equals the rate at which this one increases. That's going to give you the low point. And then this is going to decrease even less rapidly. This is going to increase more rapidly than this one decreases. So the total time is going to start coming up. The point at which we get the low point, well, the low point of the curve, and this is in the document. I've included a reasonably good graph. It was created by Excel, and I didn't have time to muck around with Excel to make a nice smooth graph. You just about can't do that with Excel. And I don't have the software in this machine to do it right. But still, you can see from the graph that this curve keeps decreasing and probably comes very close to leveling off here. It actually does level off at the very last instant. This one keeps increasing, and the way this one decreases and the way this one increases combine to make this one reach a low point here and then tail up just slightly between here and here. The other thing I'll point out about these graphs is that this graph is the sum of these two graphs. If I take the y-coordinate here and add it to the y-coordinate here, what do I get? Well, I add this to this, and I get the y-coordinate here. Okay, over here, I take the y-coordinate here, add it to the y-coordinate here, so this y-coordinate adds to this y-coordinate to give me the y-coordinate on the white graph. So you can see this graph gets higher, so I'm adding more to this graph than I was at the beginning, which means that this graph is going to get further apart, this graph and this graph are going to get further and further apart. You should try to think about what I just said and see if you can't come to a good understanding of how this graph plus this graph gives you this graph. Okay, and I'll also say that the, okay, here's the low point of the curve, and that occurs at some value x. That's how far you go along the beach to achieve the minimum time. Delta T min is the time, the minimum time, because of course the delta T axis is up here with the x axis here. So the minimum time is going to be whatever we get when we project over here. And it turns out that for this curve, the minimum time is about 99.12 seconds, okay? And to achieve that, X is about 175 meters. You run down, and the last 25 meters, you just jump in the water. You aim for the point 25 meters short here. You jump in the water here. I'll also comment that if you throw there's a dog I like to throw sticks for. She'll go hours in the water. She's half Labrador and just loves the water. If I throw a stick, if the shore's along this line, and if I throw a stick out there, she will go down the shore to pretty close to the optimal point before she gets in the water to go get that stick, because she wants to get that stick as quickly as possible. Now, early in the process, she might tend to go more toward the straight line because she's just focused on getting to that stick. But after a couple of times, she gets the idea that if she goes out a little further here, she gets to the stick more quickly. And it's been studied, and dogs do a really pretty good job of figuring out exactly where they should go in the water to get to the stick. Now, later on, when she's getting tired, it takes a long time to tire her, but she gets tired, she'll go out to here just to minimize the swimming distance, because swimming is a lot more energy intensive than running through the air. Moving through the water takes more energy than moving through the air. And all those things are worth thinking about, especially the way these graphs interrelate, and the fact that, well, we don't really know how to construct this graph, we don't really know how to construct this graph, and sometimes it is appropriate to use technology. But we're not going to do much of that in this course. Technology can wait while you learn to actually construct graphs and do the mathematics.